we're going to talk about airways and aspergillosis and try and put that together. And our first speaker this morning you met already because he was one of our moderators, David Corry, who's from Baylor College of Medicine in Houston. And he's going to talk about Th2 immunity, which is an interesting challenge given the IL-17 work that we heard about this morning and other things. So, David, over to you.
For doing a terrific job in this conference once again, and this year under trying circumstances, and everybody was able to travel here and those online. So when we think of aspergillosis, the first thing that typically comes to mind are the invasive syndromes we've already heard a lot about today, rightly so. I mean, these are things that move very quickly, medically speaking, rapidly fatal, basically medical emergencies. It's good they certainly do deserve our attention. But as David showed earlier in the meeting, it's the non-invasive aspergillosis syndromes that are numerically far outweigh the invasive syndromes, and so they also deserve our attention. And so it turns out that the chronic aspergillosis syndromes typically involve mucosal infections, often but not exclusively involving the airway, and they tend to be marked by a particular immune profile, that is Th2 or type 2 or allergic. So all of these terms are somewhat interchangeable, and I'll probably be doing that in today's talk. And so what I'd like to talk about today then is how you get that Th2 response. So what is it about fungi or something else in the environment that leads to the evolution of that Th2 response? So maybe that can help us think about therapeutics perhaps in the future. So what are the allergic airway mucosal aspergillosis syndromes? So a couple we've already talked about to some extent already in this conference: allergic bronchopulmonary mycosis or aspergillosis. A closely related disorder of the upper airway, allergic fungal rhinosinusitis. I think most of us would agree these are aspergillus or fungal-related disorders. But there's many others that have similar characteristics and certainly have a very similar immune profile that maybe are not as well known. On the severe side, Churg-Strauss syndrome, which begins as an asthma-like disorder, but then takes on a systemic character, autoimmune-like, involving a granulomatous vasculitis that can affect almost any organ. Chronic eosinophilic pneumonitis is a pneumonia-like disorder that's rapid onset. The lungs basically fill with eosinophils. Again, it has a pretty strong connection to asthma, but it's just much more severe in an acute sense. There's things on the mild to moderate side that are not fungal related. So tropical eosinophilia syndrome, Loeffler syndrome, these have been more clearly linked to parasitic worms or parasites of some form that get lodged in the lung. Loeffler syndrome has also been linked to drug hypersensitivity reactions. And then there's eosinophilic bronchitis, which is basically some eosinophils in the airway. Maybe you have a little bit of cough. But most of these disorders do not have a clear link to fungi. And then in terms of prevalence, though, and incidence in most populations, by far the most common are chronic rhinosinusitis, which has many features that overlapping with allergic fungal rhinosinusitis, but less severe, and of course asthma itself. And then, so there's always been some question with these disorders as to how fungal related or not they may be, and we'll come back to that in just a moment. But in thinking a little bit more about that allergic response, so just arranging some of the cells and molecules that have been very clearly linked to allergic inflammation of the respiratory tract, and then trying to fit that into some immunopathologic scenarios. Beginning in the 1970s, the mechanisms underlying type 1 hypersensitivity were worked out by Ishizaka. So the key cell here is probably the T helper type 2 cell that secretes a restricted repertoire of cytokines like interleukins 4, 5, 6, 9, and 13. IL-4 particularly important in driving that IgE response. IgE is captured by high-affinity receptors on things like mast cells and eosinophils, and it's cognate encounter with that antigen that leads to the degranulation of these cells, releasing histamine proteases, leukotrienes, many other secondary mediators that lead to the key features of asthma, including airway hyperreactivity, goblet cell metaplasia, mucus hypersecretion, and probably mucosal edema, all contributing to that airway obstructive phenotype, which is obviously a key feature of this disease. But beginning in the 1990s, another very important disease mechanism was revealed, more of a type 4 hypersensitivity process, in which Th2 cells now assume a much more direct role in disease pathogenesis. They secrete 4 and 13. that signal through a substantially similar receptor that includes the alpha chain of the IL-4 receptor and activate a key transcription factor, signal transducer and activator of transcription 6, that actually appears to be more important in driving these airway obstructive phenotypes, probably overriding type 1 hypersensitivity, so we now think today. So here's some of the older cells and molecules linked to type 2 immunity. But then there are even newer players, more on the innate and adaptive side. So these epithelial cytokines, IL-25, IL-33, thymic stromal lymphopoietin. There are now a new class of innate immune cell called innate lymphoid cells, types 1, 2, and 3. Th17 cells we've heard something about today, and then T follicular helper cells I mentioned briefly. So there's a lot going on here, and this is only a subset of all the different allergy-related cells and molecules. We don't have enough time to put this all together in perspective, and that's really not my intent today. I'd rather focus on what is it that's more fundamental. What are the things that come out of fungi and perhaps other sources that lead to the genesis of this type of complex inflammation? So to answer that kind of very fundamental question, we need to dive deep and look at histologically what asthma is really all about. And so here's an airway from a patient who died of asthma that has some very interesting features we need to grapple with. So in addition to all the inflammation, you see tightly focused around this airway and the very abnormal smooth muscle that leads to that airway hyperreactive phenotype. There's this guy here. So this is a fibrin plug. So we now have to begin considering the clotting system. What is this clot doing in this guy's airway? In fact, it obstructed up to 90% of his airways and led to his death. And in fact, this is the main reason for death in asthma, is asphyxiation to this kind of airway fibrin deposition type mechanism. Well, we can mimic this exact kind of thing in mice, fortunately, and so we have a very robust model we can test our various hypotheses with, and I want to go through some of these with you. But before we get to the mouse studies, we need to begin thinking a little bit more about connecting the allergic disease mechanisms to the coagulation system. How does this really work, and then how does this relate back to Aspergillus? Well, it turns out that if you, a few years ago, we perfected a method for culturing sputum from folks that have asthma, and usually those using standard microbiological techniques. We talked a little bit about this earlier in this conference. Those cultures are typically negative, but with an enhanced technique, which you get over and over. And in fact, 90% of our cultures, we've done about 1,000 of these now. We actually do this as a clinical service. In my hospital, you get exactly what you might expect. Here's some Aspergillus here. There's alternaria here. And this second patient here, both of these patients, by the way, stuck on mechanical ventilators with respiratory failure and asthma, a lot of alternaria, but in this white creamy stuff is Candida albicans. Here's a third patient, an administrator at my hospital, had mild to moderate asthma. She grew out a mixture of Aspergillus and alternaria, and her sputum shows a lot of interesting features, including Charcot-Leyden crystals, which are crystals of galectin-9. It's an eosinophil protein. We know, therefore, that she has asthma. And which you might miss unless you have some training, which you can find in virtually all of these patients, is this kind of structure. This is basically a hyphal mat. It's growing. It's actively shedding spores under the microscope. So no question then that fungi are very, very, very commonly and robustly linked to garden variety asthma, so either severe asthma or even mild to moderate disease. So not a whole lot different than from the standard disorders we've known all along are related to fungi, including allergic bronchopulmonary aspergillosis. So that's all. So you can grow a few fungi if you do centered culture methods, but if you take a metagenomic approach, and so here now we're doing PCR-based ITS2 region amplification, what we find is, in terms of operational transcriptomic units, which is the genomicist term for species, we find not just 2 or 3 fungal species, and we find in this patient here, for example, looking at his sputum using this technique, 12 different species, and this guy here, almost 60 different species of fungi. So this is not like tuberculosis, it's not like influenza, which you have a single pathogen causing a respiratory disease. You have up to many dozens of the same kind of organism. So this is not, your average infection. It's not a zombie apocalypse, but it's the fungal apocalypse, right? So it's kind of a scary endeavor. In terms of what kind of species we actually see? Well, certainly there's people that have a lot of Aspergillus. In fact, most of these people are growing, or at least we can find Aspergillus DNA. But some folks are predominantly yeast growing, like this gentleman here that has Candida. But most of our patients, and this is just a limited sampling, have a rather wide diversity of fungal species, including things I never even heard of until we got these results, like Nicasiomyces and Trametes. Okay, so we don't know who is pathogenic here and who is not, but we can switch now to the mouse. We can take up to 13 or 14 of the kind of species we isolate from humans. We can give these to mice. So what we're doing here is we're sporulating each of these different fungal isolates. We're taking 400,000 Canidia and giving these intranasally to mice. And we're looking for airway hyperactivity. Thank you, Kurt Dury, for showing some of these data earlier, so I don't have to explain in great detail what this is, but we're looking at airway hyperactivity in the mouse by measuring respiratory system resistance, plotted against increasing amounts of acetylcholine injected intravenously. We'll leave out Curvularia here because it's a very strange fungus that's very different from all the others. It has a very strange pattern here. The others are rather similar. They all induce airway hyperactivity compared to our negative control here. Some of these guys you may not have heard of, like Chromosporium olari, but the ones that are very strong in inducing that airway hyperactivity, you certainly have heard of this, multiple Aspergillus and Penicillium species. So looking at the mouse model, we have never found a non-pathogenic fungal species. They all can induce airway hyperactivity and type 2 immunity to some extent. So again, maybe all the fungi that are in the human airway in asthma and other respiratory tract allergic syndromes, they're maybe all contributing to that disease. We just don't know. So in terms of, though, what is coming out of these fungi that induce this phenotype? Well, we've known this for about 20 years now, and that is the protease, probably the most important virulence factor that comes out of molds that drives that type 2 response are their secreted proteases. So this is just a limited set of data we've developed more recently. Here we're giving to mice intranasally the protease derived from Aspergillus oryzae. This is a commercially available product that's very easy to get and works very, very well in mice. So we're giving about 7 micrograms of this protease every other day for a couple of weeks, and we get very nice airway hyperactivity relative to our negative control, as you can see. Things like eosinophils go from 0 to several million in bronchoalveolar lavage. Here's IL-4 producing cells. There's 0 in vehicle-challenged mice, and these go up to several tens of thousands. And MUC5AC is the major mucin gene expressed in the human and the mouse airway, and this can go up to 60-fold higher after receiving that protease. We get very high levels of IgE and everything else that you might want to see in terms of an asthma-related endpoint. So just a single molecule can replace everything that the entire fungal organism can do. We can do other things to help us prove, and there we go, finally moved. We can do other things to prove that, in fact, that protease is essential. So in these experiments, we're looking at wild-type Aspergillus niger now. Niger is the most common fungus in the homes of children that have asthma in the Houston area where I'm from. Wild-type Aspergillus niger gives excellent airway hyperactivity in mice, but these two variants here, one is missing the major secreted aspergillopepsin, so it's down to 30% residual secreted protease activity. The other mutant strain is missing a regulatory element that controls all protease secretion, so this mutant here makes no secreted proteases. These two variants, then, that are protease defective, are incapable of inducing airway hyperactivity in mice, no matter how hard you try, how many spores you deliver, that kind of thing. In terms of looking at that inflammation, eosinophils coming in out of bronchoalveolar lavage, the absolute numbers very strongly depend on the absolute amount of protease that these fungi make. And then looking at cytokines, so here's IL-4 production and interferon gamma production, and here's the IL-4 interferon gamma ratio. That ratio varies up to 40-fold, depending on exactly how much protease these fungi make. So that protease then is essential in driving that type 2 immune response and therefore the virulence of the resulting disease in this experimental context. So let's turn now then to the molecular pathways by which fungi induce allergic airway disease. And we're particularly going to focus then on how that protease induces this canonical inflammatory response. So we mentioned in the earlier slide that fibrin deposition is a big part of what asthma and other allergic inflammatory disorders is all about. So the key clotting factor, of course, is fibrinogen. Here's what it looks like schematically. It's a very interesting molecule. Fibrinogen is, first of all, it's one of the most abundant proteins in serum, and it's comprised of 3 different polypeptide chains, alpha, beta, and gamma, and they're arranged in a dimer configuration. So this is really a trimer dimer. So the carboxy termini come together at 2 parts per molecule to create what's called the D domain, and the N termini come together to form what's called the E domain. And as you know, fibrin is what results from fibrinogen after the activation by thrombin. Fibrin clots are degraded by other endogenous proteinases, such as plasmin, to release a variety of degradation products, fibrin degradation products, or fibrin cleavage products, that we can use diagnostically to look for disorders of hemostasis, for example. But we wanted to know what happens in the context of fungal proteases to fibrinogen. So this is a fibrinogen degradation assay. We're mixing whole fibrinogen, human fibrinogen, with a constant amount of the protease derived from Aspergillus mellitus, and following this over time. So as you can see, out to about 10 minutes, fibrinogen is losing molecular size, but we don't see any distinct bands until we get to about 30 minutes. And then you begin to see these 2 bands, it's 150 and 75 kilodaltons, showing up consistently out many hours. And after 24 hours, though, the molecule is pretty much shattered. So it turns out that these molecules are immunologically quite important. I'm not going to walk you through all the basic science. I'll just kind of schematically represent what we found. That D domain, which can be found in the serum of people that have a variety of inflammatory disorders, including asthma, up until recently, it was just an observation. It had no function that anybody is aware. But here's how we think about the D domain now. I'm having a little trouble with the electronics. There we go. We think of it as, again, fibrinogen is a trimer, alpha, beta, and gamma. We view this now as a beta-gamma core that's relatively protease resistant, surrounded by a highly protease susceptible alpha chain. Fungal proteases acting on that alpha chain remove it entirely to reveal that beta-gamma core that then has immunological significance, whereas the D domain by itself does not. So it ends up turning out that this is the beta-gamma core ends up acting on toll-like receptor 4, and this is our model for how this works. The beta-gamma cryptokine, or hidden cytokine, then interacts with the integrins MAC1, which is CD18, CD11B. This trimolecular unit then is competent to engage toll-like receptor 4 to induce 2 different kinds of signaling events. The first is activation of STAT6. I mentioned earlier this is a key transcription factor activated by IL-4 and IL-13, and which drives expression of allergy-related genes. And a second event that happens is activation of NF-kappa B, and NF-kappa B is very important in driving antifungal immunity. Let me show you just a little bit of data to show you how this works. If we simply prepare fibrinogen cleavage products, FCPs, by cleaving fibrinogen, mouse or human, with the proteinase derived from Aspergillus oryzae or other proteases, what we get when we challenge mice, not with fungus, not with protease, just the fibrinogen cleavage products, we get, after a couple of weeks of challenge, we can get significant airway hyperactivity in red. That's in wild-type mice, but if we do the same thing in blue to STAT6 knockout mice, you cannot get that airway hyperactivity. So the activation of STAT6 just by FCPs with otherwise no other activation of the innate or adaptive immunity is sufficient to drive an asthma-like phenotype. In terms of inflammatory gene transcripts, IL-13 receptor alpha-1, one of the major receptors for the IL-13 receptor, goes markedly up, as does MUC5AC and arginase 1, a marker of type 2 IL-4, IL-13 activated macrophages. In terms of inflammatory cells in bronchoalveolar lavage, we get a substantial increase in inflammatory cells that is markedly reduced in the STAT6 knockout. And then in terms of inflammatory cells, again, marked increases in neutrophils and significant increases in eosinophils in wild-type mice, but most of that is abrogated or markedly reduced in the STAT6 knockout mouse. So the type 2 immune response can be induced through simply cleaved fibrinogen, resulting from the interaction of fibrinogen with fungal proteases. What about that NF-kappa B activation? So we struggled with this for a while, but it turns out what NF-kappa B is doing is acting on cells like macrophages, and here we're culturing bone marrow-derived macrophages, and we're stimulating them with those same fibrinogen cleavage products. And then we're deliberately contaminating these cultures with about 100 spores of Aspergillus fumigatus, and we're looking to see how well these macrophages then kill those fungi. So before we add the spores, we're activating these macrophages with a variety of things, including lipopolysaccharide. The fibrinogen cleavage products derive from the activation of the protease from Aspergillus mellius, or this is the Dermatophagoides farinae, a dust mite-derived protease, and this is thrombin-derived fibrinogen cleavage products. It doesn't matter how you get your FCPs, they all induce significant improvements in the ability of these macrophages to control the growth of these fungi in vitro. We think what's actually happening, we haven't quite proven this, what the FCPs are doing is they're signaling through NF-kappa B to induce secretion of antimicrobial peptides. We think this is clinically relevant because if we take that same assay and now we adapt this to humans, okay, so these are peripheral blood monocyte-derived macrophages in culture from healthy controls, those with chronic rhinosinusitis with nasal polyps, or those with the more severe allergic fungal rhinosinusitis. What we see is that the ability of these different patients' macrophages to control that fungal growth very strongly depends on their disease status. So even after all the activation we can give in terms of adding FCPs to stimulate these macrophages, whereas virtually all healthy people that have no allergic disease can completely control that fungal growth, there is about half of CRS with nasal polyps do just fine. A few have moderate defects and a few more have severe defects. But when you get to AFRS, the majority of these patients are either mildly or very severely impaired in their ability to control that fungal growth in vitro. So we think this pathway by which cleaved fibrinogen signals through toll-like receptor 4, activates NF-kappa B, an innate antifungal program, we think this may explain some of the apparent inability of these patients to control their fungal growth, leading to the chronicity of their allergic disorders. So we've seen that fungal spores then, inhaled, begin growing along the airway. They secrete proteases that drive a Th2 program. And then a chemokine program from epithelial cells of the airway that drives recruitment of Th2 cells proximally to the airway, and they begin secreting these cytokines IL-4, which drives IgE production, but also alternatively activated macrophages. IL-5 drives those eosinophils, and IL-13 is what really mediates the goblet cell metaplasia, mucus hypersecretion, and the airway hyperactive phenotypes. So we thought this was a pretty good scenario, but now we've realized that there's a whole bunch going on in the middle that we need to start thinking about further, and that is what we kind of just talked about. Fibrinogen gets into the airway from the serum. It's also made by airway epithelial cells, and once cleaved by those fungal proteases and the FCPs start falling off, they can engage macrophages to make them highly fungicidal. The same thing happens with airway epithelial cells. But fibrinogen cleavage products signaling through TOL4 on epithelial cells also drives upregulation of IL-13 receptor alpha-1, without which the IL-13 from those Th2 cells cannot act to induce asthma-like phenotypes. And so we have innate and adaptive cooperating to give you the full phenotype. But where do those Th2 cells come from? We're still working on that. But this was a very important paper from 2017 from a developmental biology group, Chi et al., that made this, I think, this very fascinating discovery. These investigators have been studying Wnt pathway signaling, and they made, since 1998, it's been known that platelets, for example, are very important secretors of Wnt pathway, both agonist and antagonist peptides. What they found is that one particular Wnt pathway peptide made by platelets called DKK-1 is secreted from platelets during allergen challenge. So in their initial study, they used dust mites and parasites to demonstrate this, but what they found is that those platelets under this kind of allergic challenge, or at least DKK-1, that feeds back to secondary lymphoid organs, where CD4 T cells are located, and drives the emergence of Th2 cells. And furthermore, these Th2s are recruited back to sites of chronic type 2 inflammation, again, to drive the chronicity of these disorders. But we wondered what's happening in terms of Aspergillus proteases. So we're still, again, working on this, but I want to share some very brief preliminary data. Here we're looking at Aspergillus niger spore challenged mice. which get excellent airway hyperactivity if we challenge them over 2 weeks. But in green, these are mice that have been depleted with a monoclonal antibody directed against the mouse platelet that deplete them substantially, although not completely. And as you can see, we get a significant reduction in airway hyperactivity. And in this other model, here we're looking at ovalbumin-specific Th2 cells secreting IL-4 after immunizing mice with ovalbumin over 2 weeks. And here we're again in red, we're looking at platelet-depleted mice, and we can see that there's reduced production of those Th2 cells. But if we add back recombinant DKK-1 to mice that have previously been platelet-depleted, what we get is a marked enhancement of those ovalbumin-specific Th2 cells. So we think that DKK-1 from platelets actually may be exceptionally important in driving, again, that adaptive side of Th2 immunity. But we'd have to do further work to fill this out. So again, the whole Th2 or type 2 immune response is rather complicated. It gets a little distracting, but we can simplify this if we go to a more fundamental level, thinking about what actually drives that complex inflammation. So in the context of aspergillosis and other mold-dependent allergic airway diseases, we think that locally secreted proteinases drive that type 2 or allergic immune response. And that the coagulation system has been overlooked. This is an exceptionally important part of this whole paradigm. So that fibrinogen acts on the innate immune side to drive that allergic inflammation, or at least initiate that. But on the adaptive immune side, Th2 cells, but also Th17 cells, platelets are likely drivers of that cognate response through the secretion of a variety of different Wnt pathway peptides. But this part clearly needs some additional work. And the challenge for the future, though, we can talk more about this if you have an interest, but a potentially interesting way of dealing with the excessive inflammation that's often seen and inflammatory allergic disorders of the airway is inhibiting that inflammation in a way that's very specific, that is through an inhibition of some of these coagulation pathways. But you can imagine the challenge that we face. So we can't eliminate fibrinogen from people. They would become hemophilic. And you can't eliminate platelets because they would, again, have a big problem with bleeding. So the challenge for the future then is figuring out how to intervene in terms of the coagulation system to block or at least reduce that inflammatory phenotype without compromising our ability to clot. And I'll stop there. Let me thank the many, many people that I've worked with over the years that have helped put a lot of this work together, both locally and internationally. And I'll be happy to take any questions.
So any thoughts or questions on this interesting issues raised? Yeah, Ashraf?
In the asthmatic lungs, do you actually see the amounts of proteases that you would expect in your being released from the fungi compared to what you add, recombinant proteases?
So the question is, do we see the same kind of amount of fungal proteases? So we have not looked at that, but we saw that in the earlier talk today. Kirk Drury has looked immunohistochemically at fungal proteases in the airways of patients from mild, moderate, and severe, and sees certainly a dose response. But it's very difficult to quantify the exact amount of those proteases. And it's the activity that's actually more important, and that's even harder to quantify because there are many endogenous proteases in bronchoalveolar lavage and lung biopsy samples. So it's almost impossible to separate the fungal protease activity from the endogenous activity. So it's a technological issue. So I can't really answer your question, but I hope I've given you a good excuse.
Your fibrinogen cleavage product model, is that also platelet dependent?
So which model?
The FCP challenge model, where you just use the...
The FCP model, yeah, that's a great question. Let me go over that. So the FCP, if you're just giving FCPs to mice, there's no protease activity involved there, and you do not get an adaptive immune response. That's just purely, strictly an innate immune response. So no, the answer is we do not get that adaptive side, and part of the reason for that is there's no antigen, but there's also no platelet involvement. Yeah.
Strictly innate immune response.
Strictly innate, right.
Okay, Rick Moss.
That was great, David. What do you think the role of the antiproteolytic system in the airways is, and have you looked at that specifically?
That's a great question. So what about antiproteases? There's things like, there's a proteinin, alpha-1 antitrypsin, and then secretory leukoproteinase inhibitor. These are some of the many antiproteases that are found in the mammalian airway. What are they doing there? Certainly these things do act on endogenous proteases, but you got to wonder, maybe some of these things are evolved to maybe take on some of these organismal proteases. So in addition to fungi, of course, there's parasitic worms go through the lung. And so there is some evidence, in fact, things like SLIPI, secretory leukoproteinase inhibitor, alpha-1 antitrypsin, they do have some ability to inhibit fungal proteases, but they're not very good at that. It may be that it's just an intractable issue. It's hard to evolve an antiprotease in ourselves that selectively targets fungi, but again, there's dozens of fungi. They all have different proteases. So it's hard to come up with a combination of antiproteases, evolve them in a way that allows you to cover that broader range of organism, right? At the same time that you can't be inhibiting your own endogenous proteinases that are very important for biological function. So it may be that it's just an intractable issue. But it does raise questions of, pharmacologically, maybe that's something that we can do. And in fact, there are a number of antiproteases that have been found, either naturally occurring or synthetic, that have very broad spectrum activity against organismal proteases, including Aspergillus proteases. So hirudin, which comes from worm, liver flukes and that kind of thing, is actually very, very, very good at inhibiting fungal proteases. And it used to be used commercially. It used to be a pharmaceutical agent for blocking platelets and coagulation in the perimyocardial infarction period. Has been taken off the market, but nonetheless is very good. So it sets an example that maybe this is an area we could do a lot more work in. So we'll see.
So I managed to acquire one question online, which is the first for this meeting. So Peter Cork, who's going to be talking next, actually, asks about the FCP work, and he's wondering which cells express STAT6. Do you think it's epithelial cells, macrophages, T cells,
Sure.
or some other cell?
So just about every cell, that's a very good question. Just about every cell has STAT6, and virtually every cell has IL-4 receptor alpha, so IL-4 and IL-13 can act on virtually any other cell to activate STAT6. But in terms of FCPs, well, that's a little different. So you have to have CD11B, and CD18, the MAC1 integrin, plus toll-like receptor 4, for FCPs, for example, to be able to activate STAT6. That's a much more limited number of cells. Typically, mostly that's confined to leukocytes, things like macrophages, but also lymphocytes, and even epithelial cells can express CD11B. Most cells express Toll4, but it's that C11B that limits how the kind of cells that FCPs are going to work on.
Okay. And then I have one hopefully a quick question, quick answer, I don't know. You described before environmental protease from Aspergillus niger inducing allergic inflammation. But in the models that we've put forward, it's probably because you have colonization or infection of the airways, which is ongoing producing proteases. Right. So do you think both those systems are operating? Do you think we breathe enough protease in from the environment to drive this, particularly in a moldy, damp environment, other than like a clean environment? So what is the relative balance between colonization proteases versus external or exogenous proteases?
Great questions. Yeah, so maybe just to summarize. So is it the fungus chronically or just repeatedly infecting the airway or colonizing the airway, producing that protease in situ, or is it the protease in the carpets that we're inhaling? So we actually did some of that work. We actually went into 200 homes of kids that have asthma in the Houston area. We vacuumed their houses. So imagine that, you got a vacuum cleaner in your back, and you go up to some house, you rap on that door, say, "Excuse me, can I walk in and vacuum your carpet? And by the way, I'll give you a $50 gift certificate." So it's the easiest study ever. Nobody ever said no. So we vacuumed those houses, looked at that dust, and And there are proteases in just about every house that we went into, but the proteases, to the extent that we can define this, are all coming from fungi, and it's all coming from pretty much Aspergillus niger. And again, that's why we focused on niger. So that led us to wonder, okay, so knowing how much protease is in the carpets and trying your best to estimate how much a kid, on all four going under mom and dad's bed sniffing, dust bunnies all day long, maximizing the kind of protease that they're likely to be inhaling, and now going back to that, of course we can't do these in kids, but we go back to the mouse and mimic that same level of protease activity. And I can tell you that it's absolutely nowhere near enough to induce allergic airway disease. It's not even within 2 or 3 orders of magnitude enough. Right. So it's there, the proteases are there in the carpets, but it's just there in trace amounts. Yes. So that's what actually got us thinking more of an infectious or a colonization type issue. Okay. So there is data, of course, that comes out of UK from the late 60s, right, where laundry detergents at that time were just starting to become more diverse. People were adding bacterial recombinant proteases to make those detergents work better, and then a lot of asthma started coming out of those factories, not in just anybody. The guys who were handling the proteases were coming down with a lot of that. So anywhere proteases are used in industrial scales, there's a lot of asthma. That's a big occupational problem. That's how we know that the proteases by themselves are relevant to humans, and yes, just simply the fact of inhaling aerosolized protease can give you asthma, but those are industrial problems. The domestic context, I think, is quite different. There's nowhere near enough of that protease in the environment. We think it's really a colonization or infectious issue. I hope that wasn't too overwhelming.
No, I think you've answered the question. Okay, thank you very much, David. We'll move forward. So we now have